Hi students, this next question, question number 2 from the May 2025 exam paper 2 time zone 1 is addressing the concept that you have learned in the unit D.1 about the gravitational field. Okay, so let's start from this diagram. As you see that it the Venus and the Earth, as you know, they rotate around the sun. So we are given the time periods: 225 days orbital period for the Venus and 365 days for the Earth. What we have to find out, we have to find out the ratio of RV to the RE. Okay, their orbital radius ratio. So these, so they rotate around the sun in their respective orbits. So they, of course, they take a different time. Why? Because they have a different force of gravity from the sun. So this is RV, this is the orbital radius of Venus, and this is the orbital radius of Earth, right? Which is 150 million kilometers. We have to take a ratio. Okay, now since this question is about the planetary motion of the solar system, inside the solar system, so we can apply Kepler's laws, right? So in fact, the Kepler third law exactly gives us an equation, right? What the Kepler third law is about, it says that the square of orbital period is proportional to the cube of orbital distance, which means that if a planet will be far from the sun, so its orbital distance is very large, then it will take more time to complete its one rotation, right? And we observe the same thing. Okay, so here right now, in order, because we have to find a ratio, so we do not need to go in a detail about the what is a constant. So right now I'm just writing k. In the next question I will explain you how to find the k as well. So can I say that if we want to find a ratio, so it means that RV cube over RE cube is equals to TV square over TE square, and the constant will be cancelled out because that is the same. So we can write it like this: RV over RE raised to power 3 is equals to ratio of their orbital time periods and its square, right? Since we just want to find the fraction of their orbital distance, and you must take a cube root, right? Because if we take a cube root to get rid of this cube, we will take this cube root on the both sides of the equation as well as on this side. Okay, so this is a cube root. So what we will get as a result, we will get RV over RE is equals to TV over TE raised to power 2 over 3, right? Now we are given the time period, orbital time period, in days. You don't need to convert it into the seconds because we are having a ratio, so it will just cancel out, right? So it is 225 over 365. Okay, so even if you convert days into seconds, so that number will cancel out in a fraction. So if you take a 2/3 of this, right, let us check what answer do we get. So our answer should be in terms of three significant figures. So that is 0.724 without any unit. Okay, and here is what Mark's scheme says: Kepler third law, and this is a ratio. Okay, now let's move to the next question. Explain how observations of motion of planet allows scientists to determine the mass of sun. As I have already explained you that the Kepler laws of motion, they basically represent the planetary motion. They talk about the orbital shape of the planet. It talk about the relation of the time period or orbital distance, right? And area swept by the planet. Okay, but here, how can we find out the mass of the sun? This is, we can find out it qualitatively as well as quantitatively. So let us understand how can we find out this mass. So if you straight apply the Kepler's third law, right? Let us solve this thing over here. So Kepler's third law is T square is equals to, as you know, is a constant times R cube. That constant is actually 4 pi square over GM, right? r cube. There will be a little bit, I will go irrelevant, but I will explain you how you can get this equation. Okay, so from this equation, this m is a mass, this larger m is a mass of sun. So you can find this mass of sun quantitatively from this equation, 4 pi square t g t square. So now you know the orbital, I mean, right now we don't know the orbital distance of Venus, but we can represent it into the form of, because look, let me explain you. So it is equals to 4 pi square r v cube over g t v square, and it can be written as equals to 4 pi square r e cube over g t e square. Okay, so it's just an extra explanation, but you understand how can we find the mass from the Kepler's third law. If you want to derive the equation of Kepler's third law, right, I just give a clue that because when these two planets are revolving around the sun, so remember, actually their acceleration is towards the center of the sun, and we call this acceleration gravitational acceleration or gravitational field strength. Okay, and you know very well that this gravitational field strength is equals to centripetal acceleration, and that is equals to v square over r. Since this is a gravitational field strength, so you know it is the force per unit mass, and if you remember its equation, it is gm over orbital distance square is equals to v square over r. So if you further put the value of v, that is the average speed, and that is equals to 2 pi r over t. And when you will apply this value of v here and you will simplify it, you will soon get this equation, t square is equal to 4 pi square over gm into r cube. Okay, let's get back to our question. So students, here is the mark scheme. Let's see what they say. Suggest an equation that combines r, t and m, so you can apply this Kepler third law to find this mass of sun. Okay, now let us see the last part of the question, which is just specifically for the HL students. SL students can go to the next question video. So as you see in this question, they say the difference between the maximum and the minimum earth sun distance is 5 times 10 to the power 9. So here we are categorically taking the fact into an account that the earth does not revolve around the sun in a perfect circular orbit. Okay, it have a minimum distance and a maximum distance. I will show you in the diagram. So dear students, let's say, just imagine, although it's not that much elliptical, let me. So students, I think now this is a better diagram. As you see that if I find this distance, so let's say this is the r max. Okay, r max, and when the earth will be right at this point, so then this distance is r minimum. Okay, so force of gravity also varies proportionally, right? So okay, so in this question they say the difference of these two distances, delta r, is 5 times 10 to the power 9 meter. Okay, whereas because there's a difference of distances, so there will be automatically the difference in gravitational potential, because gravitational potential, which actually is a work done on the object having some mass to take it from infinity to a certain point in the gravitational field. This is the absolute gravitational potential. But in simple words, we can say gravitational potential is a work done per unit mass. Okay, so it depends on the mass as well, right? So this is the delta v, which is equals to 3 times 10 to the power 7 joule per kg. Okay, now we can represent the potential, gravitational potential, in the form of gravitational field strength. That's why they are asking here to find out its value, right? You know that the v is equals to negative gm over r. If I multiply with r and r, so that will be equals to negative gm over r square times r. Now you know that this gm over r square is the gravitational field strength. So we got a relation that links the potential with the field strength. Okay, so this is an equation that is the basic and fundamental equation. Now I am going to write the change in potential, because we are given the change in potential, right, is equals to negative g into delta r. So dear students, you see one thing, that the g is equals to negative of the potential gradient. Interesting concept. The field strength, gravitational field strength, is always equals to negative of potential gradient. It means that if you take a graph taking the potential on y-axis and distance on x-axis, the slope or the gradient of that graph will be equals to negative of g. All right, you don't need to, I mean, we must not ignore this negative sign. Okay, so now we will just simply apply the values here. So we got g is equals to negative 6 times 10 to the power negative 3 meter per second square, or Newton per kg, are basically the same thing, right? And let's see what Mark's scheme says. So Mark's scheme says that apply this equation, but I have gone in too much detail to explain it very well, the basic concepts and the background knowledge, with the help of a diagram. I hope this works, and see you next question. Take care. Bye.